Hi, welcome to the University of Sydney. My name is Sergio León Sabal. I'm the director of the Sydney Astrophotonics Instrumentation Laboratory. And we are based at the basement of that School of Physics, which is the building there in my back. And today I'm very excited to show you a few different things that we're doing around the labs. We're going to be looking at the latest instrument that we're building for the 4-meter telescope in Australia, which is called Hector, with over 3,000, 4,000 fibers on it. And we're going to be looking also at the technology that we use for fabricating aperiodic fiber Bragg gratings. And also we're going to be look how and where we fabricate specialty optical devices like photonic lanterns, hexabundles. And we're going to also look into the latest developments that we're doing in astrophotonics for imaging interferometry and exoplanet detection. So follow me. Hi guys, welcome to the basement where the cool stuff happens.
Hi, welcome to the Sale Glass Processing Lab. This is where we make devices like the photonic lantern, other multi-core fiber devices, things like the hexabundle, which is a large bundle of fibers for astronomy, which you'll hear a bit more about later, and other tapers and devices for sensors that get used throughout the university. This is the main workhorse of our area. It's our fiber taper machine, and you've actually caught me in the middle of making a photonic lantern device right now. Which is actually made from a multi-core fiber and then a glass capillary. So what you should be seeing here is a top-down view of the taper process happening, where we've got the two stages, both moving at slightly different speeds to get our taper shape right. And in the very middle, there's this kind of purple region, which is actually a heated plasma that's formed between the three electrodes. The nice thing about this is that you get this nice large heating zone, which means you can make very large devices. And it also means things can be a little bit more repeatable and generally a bit easier to manufacture the same thing more than once. What you'll be seeing here is the taper process happening sped up, because the actual taper can take 3 to 5 minutes, and I'm sure you don't want to sit and watch that the entire time. And at the very end, you'll have this nice, very fine point, which becomes our multi-mode input of our photonic lantern, and the other end is our single-mode inputs. And if we get the taper just right, we'll have a nice, efficient conversion from several single-mode inputs to one large multi-mode input, or can be used in reverse, of course. After that's all done, we would cleave at the tip down the end, package it up in lots of glue to keep it nice and safe, connectorize the other end, and then ship it off to a telescope or include it in one of our instruments.
Hello, welcome to the Advanced Fiber Fabricating Facility at the University of Sydney. This facility comes from many years of research and development here. And this facility can write gratings of arbitrary phase and the amplitude design. This is a typical example of the amplitude. The red line is amplitude, the blue line is the phase. So you can see the phase amplitude can change very much, a lot. And a typical example of this grating is the astronomical sky-OH filters. And that's the one we pretty much unique to make this. Also, this facility can write a very wide range of kappa and phase. You can change it from a low index change to high index change, stronger grating or weaker and longer. And also, these grating products can come from band filters and any high resolution of rejections and fiber lasers, all kinds of products.
Hi, welcome to the Fiber Preparation Labs. I wanted to show you some of the devices that we've got for the Hector instrument. Hector is a multi-object integral field spectroscopic instrument being installed at the Australian 4-meter telescope, and it uses these devices called hexabundles developed here at the University of Sydney that are hexagonally packed fibre optic arrays that are used to both spectrally and spatially sample galaxies. The hexabundles are spliced onto longer fibre cables that then lead the light down into the spectrograph at the telescope. The hexabundles are secured onto the telescope focal plane with precision-placed magnets. These are positioned using a custom-built robot to within 5 microns.
Hi, Welcome to the fridge. So in here we have a couple of astrophotonic experiments which are really sensitive to temperature, so we're keeping them in here. The first one is a test bed for an instrument called GLINT. GLINT is an instrument that we have at the Subaru telescope in Hawaii, and it's an astrophotonic interferometer and nuller. So what we do with this is we try and image exoplanets, and the problem with exoplanet imaging is that the exoplanet is far, far fainter than the star that it's orbiting, maybe 1 billion times fainter, and it's also tiny on the sky, maybe 1/10 of an arc-second separation. So what we do here is we take the pupil of the telescope and inject different parts of the telescope pupil into different waveguides inside this photonic chip that you can see here. So this is a chip made with ULI, and in it the different parts of the pupil are interfered with each other using directional couplers. And then by adjusting the phase at the input, we can cause the starlight itself to be nulled out, revealing the faint planet light. So over here we have another experiment. So this is where we're using a photonic lantern as a focal plane wavefront sensor for adaptive optics. So in astronomy you use adaptive optics to correct the effects of the Earth's turbulent atmosphere on starlight. And normally what you do is you have a separate wavefront sensor in the pupil plane of the telescope that takes some of the light you want to use for astronomy and measures the aberrations on it caused by seeing. The problem with that is that you've got a different optical path, so the aberrations there aren't the same as what you might be seeing in your focal plane or maybe injecting into your fiber. So here we put a photonic lantern at the telescope focal plane, and as the PSF changes, affected by the atmospheric turbulence, the injection into the different modes changes accordingly, and then we can measure the different intensities at the output of the photonic lantern. And then we use a neural network to reconstruct what the turbulence was that caused that particular effect. One of the reasons that we want to do this with a photonic lantern rather than just say an imaging sensor is we're actually able to measure the phase of the PSF, because the coupling into the different modes is a function of both the phase and amplitude of the PSF.